All right, so today I want to finish up with the development of that Connect 4 program. And that should be pretty quick. And then we can talk about the final exam. But there's not much to talk about, actually. I'll just answer questions about it. Final exam covers all the material. It'll look like a combination of the 3 exams that we've already seen, plus sorting. So sorting did not appear on exam 3. We had binary search, but we didn't have sorting on that exam. So sort will appear on the final, as well as binary search. And the other similar problems that are similar to the other 3 exams. So the studying and preparing for the final is straightforward. But now what I want to do now is focus on this lab 9, which is to build this tic-tac-toe problem. And I'm showing you a process that I'm using to solve a similar problem, which is to implement the Connect 4 game. So this is it. The player chooses a column, the computer chooses a column, and we repeat that until one side gets 4 in a row. Oops. So there you go. The computer wins. And this is what we have so far. We have a text interface, unlike what I was just showing you, which is a graphical user interface. So each time the player makes a move, we print the state of the board so that we see a new version of the board. So if I take column 3, then the player's symbol is X that goes into column 3. The computer chooses a random location. It chooses 1 this time. And it looks like it's the same place that happened last time. I remember yesterday the computer chose column 1 twice. Anybody know the problem there? Why is the computer choosing the same moves?
Does it have to do with the times? Because you're not giving a parameter in order to choose your randomization of it.
Yeah, you're getting close there. So where do they? So we call rand somewhere in here, right? Right there. This is where we pick a random column. Well, we're not seeding the random number generator, so we're getting the same sequence of random numbers each time. So let's make it more challenging by seeding the random number generator. So srand. Let's pass in the current number of seconds from some epoch. And so that's we do that by calling this time function, passing in a 0. So now we're getting different results. If I choose 8, it doesn't say, oh yeah, it says bad move, try again. There it does. Control C to terminate. But what we haven't done is we're not checking for a winner, and we're not checking for a tie. So we need to add that logic. So we ask the user to go first, and then we get the user input. The user sees a grid that starts at 1 and goes to 7, but internally we convert that into a range of indices that go from 0 to 6. So we subtract 1 from the user input here. Once we get the user input, we check to see if it's a legal move. If it's not, we print bad move and try again, and we continue. So, so this continue brings execution back to the top of the loop. And now where do we check? Let's do this. After the user makes a move, let's check to see if the game is over. So if win, so the user just made a move. So let's check to see if the user wins, because the computer won't win after the user makes a move. So I'll have a function called win that checks whether the player represented by the symbol that I pass in has won the game or not. So if that function returns true, but normally just do it like this, if win. So win returns true or false. And we should also exit.
You forgot it.
Yeah, thanks. And then we'll exit as well. So we can do that by breaking. So we break from this loop. And similarly, if X doesn't win, then let's check for a tie. And then also break. So if X doesn't win, we don't need to pass it. Just tie. We just check for a tie here. And so if X doesn't win and if there's not a tie, then we let the computer move, which is here. I see. What we do here is when we move like this, I'm going to put the move there. So if the move is legal, let's take the move. And also, when we win, let's display the board. And when there's a tie, let's display the board because we want to show the move that the user made. And when the computer moves, see, if it's a tie, that means there's no open spaces. So we exit the program at that point. We exit the loop and then exit the program. But if there is not a tie, that means there's some move that can be taken. That means the computer can find that move. So we'll call computer move. Now we have to do the same thing. And we need to check to see if the computer won after it takes its move. And then we need to check if it's a tie. Actually, we only need to check for a tie in one place. Well, it depends on if the user always goes first, then there's only going to be one place where we need to check for a tie. But if we change the code and let the computer go first sometimes based on, say, a random event, then we'll need to think about when we check for ties. So just to keep it simple, let's just always check for a tie After we check for a win, if it wasn't a win, then let's check to see if it was a tie. This keeps the logic simple. Let's go ahead and stub those out. So we have a function called win that takes a character. Let's return false. And another function, which is tie. It takes no arguments. Let's return false. So once again, these are called stubs, partial implementations. Let's just see if the code that we have developed so far is all right, and it's not all right. The stubs are bad. There we go. Now it's just a matter of implementing these stubs. Let's do the tie first. How do we check to see if it's tie? Well, it's a tie, first of all, that there's no win. So it should be, let's do it like this. That x is not 1, and O is not 1. But we don't need these assertions because in our code that we've already written, we always call win first before we call tie. But just to be extra safe, I'm going to run those assertions there. So if we know that x hasn't 1 and O hasn't 1, how do we determine that it's a tie? Does anyone want to suggest the procedure? How would you determine that it was a tie? What algorithm would you use? Just looking at this, how do we know it's a tie? Huh?
The game board is full?
Yeah, the game board is full, exactly. The game board is full. How do we check to see if the game board is full in code?
Check that there are no available spaces.
Check that there are no available spaces. Do we have to check every space in the 2D array? Do we need a nested loop that checks every space? We only need to check the top row, right? So we're going to check across the columns J. So what do we check? How would you code this up? This is just like the problems on the previous exam. If we find that let's suppose we're going to check board of 0, j. So we're concerned about row 0. If row 0 is occupied by an X or an O, what do we do? Say if j is 0.
You see out.
Huh?
Typing and the program.
Say that again?
Oh, if it's full, then you're gonna see out.
No, I'm just saying this cell. Let's assume that j is 0. And we're looking at board of 0, 0. And let's suppose that there's an X in there or an O. What do we do? Can we do anything if we find an X or an O?
No, we took the next one.
Check the next one.
So we check the next one. So what if we find a space?
Then the game's not over.
Huh?
Then the game's not over.
Then it's not over. So really, we don't want to check for X and O. We want to check for a space. So if we find a space, what do we do here?
Continue.
Continue?
Return false.
Yeah, return false. So we found an open space, so it can't be a tie. We just return false in that moment. We don't have to check anything else. After we check all the columns of the first row and we don't find a space in any of them, then we return true. It must be a tie. There it is, tie, and it terminated, see?
But it's not.
So that's working. Of course, it's not really a tie, but that's because we're using a stub for the win. But we've tested the tie function and it works. Now let's implement the win function. And this is more complicated. We're going to think about the different ways to win. You can win with four horizontally, 4 vertically, or 4 in a diagonal. So let's just do one of those. Let's do the easy ones first. Excuse me. Let's check to see if there's a win because one of the players has gotten 4 in a horizontal sequence. And like how many, the 4 in a row could start in column 0, or column 1, or column 2, or column 3. 4 in a row horizontally cannot start in, what is that, column 5? No, column 4. So we want to check for 4 in a row for each row for columns starting for sequences starting in column 0, 1, 2, and 3. So we check for 4 in a row horizontally, vertically, and diagonally. Let's just implement these one after another. So to check for 4 in a row horizontally, we want to check it for rows 0 to, how many rows on there? 6. So for each row, 0 through 6, we want to check for a sequence 4 in a row, starting at column position 0, 1, 2, 0, 1, 2, and 3. Four. So basically, we're going to look for 4 in a row. If we find 4 in a row, we return true. It's a win. If we don't find 4 in a row, we just continue with the loop. So if board of ij equals the symbol and board what? What do I look at next? Anybody know? Anybody following along here? What am I going to do? What am I going to put in there? J plus 1, good. So if we find it in row I, if we find a symbol in column J plus 1, J plus 2, and J plus 3, it's a win. So that's a pretty long statement there. So we could break that up, or we could leave it long. Maybe I'll put it in 4 lines. Maybe that's okay like that. It's a little hard to format. Maybe I'll bring that down. See, that's hard. That doesn't look right. That's too hard to read. I'm just going to leave it like that.
You have an extra bracket.
Do I have an extra? Well, this should be plus.
Yeah, you have an extra bracket and you can have this. Down one.
That one looks all right.
Oh, okay.
I think that's all right. I'm not happy with the way that's formatted. Oops, sorry. So let's check for 4 in a row vertically. And it's going to be similar to this. So we're going to check, we'll range across the columns and we'll check for rows starting in position 0, 1, and 2. We'll stop at 2. There's only 6 rows. So we're going to range across the rows first. It separates those out. And then we'll range across the first 3 rows. And we'll have a similar test here. So if, I'm going to do it differently. I'm going to try to improve the readability here. Okay, let's do it like this. What are we going to call it? Call it good, say. So board of ij should equal the symbol. And board of I plus 1 j should also equal the symbol. And board I plus 2 should also equal the symbol. If it's good, then turn true. Is that easier to read? I'd like to use the word win here, but I think there might be a conflict with the function name. I think the compiler might complain about that, but I'm actually not sure. All right. So we'd want to, of course, change this. Which one do you like better? The first one or the second one?
Aren't you missing one on the second one?
Huh?
Aren't you missing one on the second
Oh,
one?
good.
If you plus 3, I plus 3. You're only checking 3, not 4.
That's because there's only 6 rows, but there's 7 columns, so they're off by 1. So
Except it's
0, 1, and 2. We can't 3. If we check rows 3, we can't check for 4 vertically because there's only 3 spaces. So 0, 1, and 2. So
Oh, no. On the board, I plus 2, you're missing I plus 3.
here?
Yeah. Shouldn't there be one more to see if there's 4 around?
Oh yeah, there's got to be another
Yeah.
one. Thank you. Thank you very much. Yeah. Thank you very much. So, is that easier? I don't know. Is it easier to read when it's listed like that? It's easier or not?
I don't know, it's the same.
I like it, like, it's not huge, like a huge difference.
What about, is this format better than this format? Or do you like this one? Better? How many people think format 2 is better than format 1? How many people think format 1 is superior? It's a tie. So I would have to flip a coin, right? So I'm going to pick format 2, so I'll be the tiebreaker. I'll leave that as an exercise to do that. All right. Check for 4 in a row diagonally. This sounds tougher. How are we going to do that? Do we do it in a loop, or do we just hard code it? You know, one diagonal sequence at a time. Because we could start, if we start here, we check for these 4. So there's the diagonal starting in this position, and this position. So 4 here would end there. So we want to go for rows 0, 1, and 2. Check for the diagonal starting in column 0. And we do that for all the way up until this column, the 4th column, column 3. So that's a diagonal going this way, and then diagonals going the other way. We're going to check the other one. Does that get all the diagonals? I think it does. So we're going to check 2 sets of diagonals. We're going to check the negatively sloped and the positively sloped. Positively sloped, and then negatively sloped. Let's do the one we just said first. So the ones that come down like this are negatively sloped. We'll do that one first. And for those negatively sloped, we actually have to do a lot of checks here, don't we? We have to start here and go down to here. And we also have to move over, and we have to do that to the very end, right? So we have to range across those columns. So we have to go up to 1, 2, 3, the 4th column. And for each of these columns, we want to start in this position, this position, this position, and that position. So, no, not this one. So position 0, 1, and 2. So stop at 3. So here, I think that does it right there. And let's do the same thing for the positively sloped. So this will be the opposite. Well, not exactly. We could keep that loop the same. We'll start, so they have to go this way. So we would want to start in column 4. or column 3. We label them starting at 0. So we want to start in column 3. And we go to the end. There's 7 columns. And for each of these columns, we want to, well, the I is the same thing. We do the first 3 rows. So that's the same. So now, instead of adding 1 to J, we subtract 1. Right? So when we're here, we need to, when we go down to look at the next cell, we add 1 to I and subtract 1 from J. So we're getting that negative slope diagonal. Did I miss any? Did we miss any? Does that get every diagonal? Can you think of a diagonal that's not hit by this code? I can't. So this problem is a little more complicated than the tic-tac-toe problem, just a little bit more. Let's see if it works. We got to spend a lot of time playing the game now. Okay, let's see. I win. That worked. Now, I think it would be hard to create an automated test program for this.
Yeah.
Now, this is the place where you would get your quality assurance team and run this thing and check it. Just play it for a day. Oh, what was that? Oh, I typed in a colon. Sorry. Run that again. See, that's what I did. Wait a minute. So I'm picking 3, then 4, and then 4. I'm going to try to get a diagonal. It says I win. What happened? So we got a bug. How come we're winning there? What did we get wrong? Well, we have to debug this thing. Let's do it like this. Well, this is going to be hard. We have to debug this.
And your horizontally, if you don't have it, the last j plus 3 one.
Say it again?
Your j plus 3 horizontally isn't set equal to symbol, so it's just sort of
Oh,
return true.
Oh. See, I was just about to fix that because I was going to normalize the style. That would have fixed it, see? But I was heading towards normalizing the style, and that would have actually fixed it. Oh, that's there. Okay, so it's I, J, J plus 1. Oops, made a mistake there. Did I get that right? Yeah, that's good. See, rather than, that was good, you caught that mistake over there. And what I was going to do was fix my style problem. And I would have spotted it when I did that. So that's one of the benefits when you refactor. If you don't know what to do, you're stuck, and your code is sloppy, or you have some kind of inconsistency in the way you've coded it, then just start working on cleaning it up, refactor, make it more expressive, make it easier to read. And then when you do that, most of the time, you find the problem. And we would have found it that time for sure. All right, let's see. Well, that may not have done it though. We're not sure yet. That's not good. The computer wins, right? So we have a problem with a diagonal test. It says you win. Oh, that's easy to fix. That's easy to fix because it's the symbol wins. So, so actually that code looks pretty good.
Just change it to.
Yeah, you lose. That's negative,
Computer
right?
wins.
Yeah. This is that's the politically correct way to do it. So it actually worked. Well, I can't win that way. And I'll try to go. Well, I can't win that way. And I'll do this one. Let's see if we can get the computer to win here. See, the computer is not smart enough to make that move, right? So that's because we're just picking a random column. So we could change that, we could fix that. There we go, the computer wins. Does the computer win? Yeah, there's the diagonal right there, up through here. Anyway, that's that. That's Connect 4. And I recommend when you work on the tic-tac-toe problem, and I'll accept submissions of that late, by the way, because it's an important exercise for you to work on.
Which one?
Tic-tac-toe.
Yes, I mean, okay.
Yeah.
Like how late?
Like Friday of finals week.
Okay, finally? Oh, okay, I'm
Yeah.
not gonna do it till
Oh,
Thursday.
Saturday, actually. Saturday finals week.
Change to Friday now.
Yeah, Saturday.
Thank you.
But now, when you work on the tic-tac-toe, I'm presenting to you a whole process. I'm not presenting code to you to look at the final product. I presented a process that we went through to solve the problem from the ground up. We didn't search the internet to look for code that implements Connect 4. We didn't do that because that's not what we're trying to do here. We're not, what we're trying to do is learn how to program. So we're reinventing the wheel. I mean, I'm sure there's tons of code out there that implements Connect 4. There's a lot of code that implements tic-tac-toe that resist the thought to go and look at how other people do it, the tic-tac-toe in particular. You need to build your skill, and you should do that by solving the problem from the ground up, just the way we did in lecture today. And remember, my recommended approach is to do it incrementally, where you do stubs, you do partial implementations, and but step by step, you arrive at a solution. So try to carry out that process. Don't take the code I have here in its final form, copy that, and try to modify it. That's not the way to do it. You're not going to learn much that way. Try to review, carry out the same process of incremental implementation that we did in these 3 lectures. All right, that's enough for that one. How about the final? What more can I say about the final exam? It's just pretty straightforward. Is there anything that I can answer about that, or do you want to look at some problems?
Yes.
Yes, some
Can I look
problems.
at classes again?
Pick a problem. Classes? Okay, so there will be something like this on the exam, right? So the number class, let's look at the exam 2. Here we go, school bus.
That's UML. Are you have UML on God bless you on the
Yeah, there will be UML. Either here I ask you for the UML diagram. So I'll either give you this and ask for the UML diagram, or I'll give you the UML diagram and ask for this implementation. I go either way. And I already did the final, but I cannot remember what I did, so I don't know which one I did.
Well, I was gonna
But
ask-
it's very easy to convert from this to this.
Yeah.
Yeah. And
All right.
vice versa.
So, yeah.
Can we implement a function that does something?
You want me to implement a function? Let's do this. Let's do this one.
Professor.
Yeah.
Is it going to be a finals going to be complete, like throughout everything we learned, basically?
Yeah.
Can we
Exams
use a book?
1, 2, and 3. The problems will look just like an exam.
Can we use a book?
No,
There's a
no.
lot to remember.
Yeah.
No, there's not much to remember. You should not be memorizing code. It's not how to do the class, I'll tell you.
Should be.
You should be practicing solving these problems. It's hardly anything to remember.
Can I phone a friend?
Well, you have to remember the sort routine and binary search. You're not going to come up with that in the exam. I know that, right? So you need to memorize sort and binary search. That has to be memorized. But when it comes to something like, scan a vector, implement a function that takes a vector, checks to see if it has all 7s, and if it does, return true, it's lucky, and if it doesn't, then return false. I mean, you don't need, you shouldn't have to memorize that solution. You should practice solving. These are very simple, beginning algorithms. And they're not simple. I say simple, but I know this is a hard class. It's not easy to do. But that you should be able to do without your notes. But binary search, I don't think you should do without your mental notes. I want you to memorize binary search. And there's great benefit in doing this without your notes. There's very great benefit. And for one thing, many job interviews, they're going to sit you down in a room and say, write a function that checks to see whether a vector is lucky or not. They'll give you that. And they're not going to give you a computer. They're going to give you a pencil and paper. And you've got to come up with the pseudocode, the rough code that shows that you understand the logic and that you can think through it. So they even check you in a professional context when you're applying for jobs. So the type of quiz I'm giving you here is in fact practical or exam. What was that question?
Could you maybe work out a couple of problems that you know from previous quarters, or problems that people typically miss?
That's what I'm trying to
Like the
get
hard
from
ones, I
classes.
guess.
How about this? Let's look at school bus. What about the constructor? You have to know how to code up the constructor. Now, the class has got 2 member variables, seats and seated students. The purpose of the constructor is to initialize those member variables. That's it. That's the main purpose of the constructor. If it does anything else, it's not a well-designed constructor, actually. The purpose of the constructor is to initialize the member variables. To do that, we could have a no argument default constructor. Then we would say set seats to 0 and seat students to 0, or set seats to 30, or whatever. But that's not going to be on the exam. So I'm going to ask for a constructor that takes the same number of arguments that we have member variables. And the job of the constructor is simply to take the values being passed into the constructor function and copy those values into the member variables. And that's what it looks like. The variable seats that's being passed into the constructor has the same name as the member variable seats. So there's a naming conflict. So you need to resolve that conflict. You have to tell the compiler that on the left-hand side of the assignment operation is the member variable seats. So this is an important distinction. This is what a lot of students are weak about, is the distinction between a member variable and an argument to a function, a variable that's declared as an argument to a function. Distinguishing between those two variables is a key. And if there's a name conflict, you need to prefix the member variable with this arrow so that the compiler knows which one you're talking about. Otherwise, the compiler will assume, if it's just seats by itself, the compiler will assume it's the variable with more narrow scope, which is the argument. That's very important to understand that, grasp that. And the other thing that, just conceptually, this class, this is a data type. We're implementing a data type. It's like an int or a string. You know, like a string is a data type. It has functions. You can call size. A vector is a data type. Once you create a vector v with a constructor, then you can call functions on it like dot size and so on. So these classes here are data types, just like vectors and strings. And so you can call the constructor many times to create many instances of the class, just like you can have more than one instance of vector class. You can have many vectors in your code. You can have many school buses in your code. If you have 5 school bus objects, 5 school bus instances, that means you have 5 of these member variables in your memory, and they're separate from each other. So once you create one school bus, it contains these 2 member variables. You create another instance of the school bus class, it contains a different a different set of variables that it keeps track of for that instance. So that's the conceptual idea that you really need to sort of get clear about. Let's look at one of these functions. So we looked at the constructor. Is any questions about implementing the constructor? That's it. And on the exam, you only need to put this down. You don't need to copy the function declaration part. You don't need this on the exam. What about add students? So we want to add students to seated students. So we've got a, huh?
And if it's more than seats, then return false, right?
Yeah, and return, so add students is, this is just the way these problems that I give you, right? In the real world, there may be other specifications that you need to satisfy. Maybe add students doesn't return a bool, it does something else, okay? So this is just for these problems that we're working on in this class. And I'll carry on, I'll keep a pattern similar to this. I'll have a function that returns a bool, and it returns false if the operation couldn't be performed as desired, and returns true if the operation could be performed in a simple, straightforward way. So we first create an instance of school bus. So you can imagine we have to call the school bus constructor to create a school bus. And then when you create the school bus instance, this school bus object, you're going to tell it how many seats it has. That's like the capacity. You know, you've got a bean jar. The bean jar has capacity. How many beans can it hold? The egg carton has a capacity. How many eggs can it hold? So that's a capacity. The number class doesn't have capacity. That's different. It's a different kind of problem. But in many of these problems, we have this that we're looking at in this class, there's a capacity. And so in this problem, seats, which is passed into the constructor, is the capacity of the bus. How many seats are there? And then the second argument is, well, when we first create this bus instance, for whatever purpose you want to use it in your code, tell us how many students are seated in that bus. It's possible that in the code you could pass in a larger number of seated students than seats. But we're not checking that in our examples, so we didn't check that. So, but we didn't check for that inconsistency, but we have been checking for an inconsistency when we call add students. There, we're checking to see whether the students we're being asked to add exceeds our capacity. Now, when we do that, we don't just compare students to how many seats there are in the bus. We have to compare students to how many available seats there are. How many available seats there are. The number of available seats are seats minus seated students. So if this value being passed into the add students function is greater than seats minus seated students, then we have a problem. That's returned false. Oh, not that one. If seated students plus students, so this is formulated in a little bit differently. Like I explained it just a moment ago, I use seats minus seated students. So you can rearrange this equation, this inequality rather, to be what I explained before. So there's different ways to formulate this. And so here it's formulated a little bit differently. Here it's, all right, take the students that are seated and add the students that you want to seat. You get a number that's more than the number of available seats, the total, the capacity of the bus. If that's the case and return false, don't do anything. Otherwise, we're good to go. Let's take the seated students variable and add the students that we're being asked to add, and then return true. And by the way, it's a little inconsistent. This is this seated students, and this is just seated students. The code is not well written. I should either add this to seated students here or omit this from here. So that's an inconsistent style. So that code is not that good. I should fix that. Now, the reason we did that is because in the specification of the problem, we say to do it that way. The add and remove functions return false and do not modify the state of the object if the operation cannot be done exactly as requested. Now, that's what I'm asking you to do. That's my specification. I could have had a different specification. I could have said, return false, but add as many students as you can. Fill up the full capacity of the object with students. Here it is. Here I'm asking for an alternative. I'm asking for an alternative implementation. So I've changed the specification. So you have to come up with a different kind of code that solves the problem. How is that? Want me to keep talking?
Couldn't hear you.
Huh?
I couldn't hear you with the door open. So I don't know what the question was. I couldn't hear you, so I didn't know what the question was.
No more questions. No more questions?
No?
Anybody? Do you want any advice?
Well, I have a question about the.
Practice.
I have a question about tic-tac-toe.
Yeah,
You were using asserts in there.
yeah.
Do you want us to use asserts? Because instead of using asserts, I was just telling them.
I don't
where
require
each-
you. I don't require you to use asserts, but I used them because, look, we had to debug the program. So asserts help you debug your code. That's the only reason. See, now, in the class, we have used asserts in two ways. We've used asserts inside test code. And we've used asserts internally, like in the Connect 4 program I just showed you, I use asserts internally just to verify my logic was correct at different points. On the exam, I'm only going to ask for you to use asserts in test code. Okay, so you need to know how to use asserts in test code. Let's take a look at one of these. Provide test code for the add students function. Use assert statements for this purpose. Make sure the test code executes all lines of code in the function. So to do, first we need an instance of the bus class. So we create it here. We call the constructor. And we're supposed to be testing add students. On the exam, the final exam, I'll show you what is this answer here is more than I require. Let me show you what I would be, well, we get a full score on the final exam. You call the constructor to create an instance, call it bus in this case. You can call it anything you want. And then you call the add students function, passing in some number, and check that it returns true. Make sure the number of students total is less than the number of seats. And then, as your third line in your answer, you call add students and you pass in a number that would exceed the capacity. And then you check to see, you make sure that it returns false. So 3 lines on the final exam. That line, and that line. That would be a minimal answer. That's the shortest answer that you could provide on the final exam for this particular problem. I don't remember what problem I asked on the final. It might be probably similar to this. Or it could be similar to the number class. I just don't remember. Okay. Yeah, question.
Will there be a curve on the exam?
Well, there's a curve on the course. And typically, and I taught this course many times, the A's are never curved. If you got 90%, you're going to get an A minus, and then A's. So you got to be over 90% to get an A. But then under that point, then everything usually I raise everything up. So if like you have 100 on your midterm, on the intermediate exams, that's a passing grade. That's not although it looks like 50%, that is really actually a passing grade. So I curve up, and when I do the final grades, I curve everybody up.
Thank you.
Yeah, okay. You were worried. I was trying to leave you worried for as long as I could. Yeah. Yeah, so that 100, if you get 100 on your exams, it's either a C or probably a C. Probably a C. That's about a C. All right, I think that's it, right? Okay, we're done.